Nice. So let's start with some examples. You can have something very ordinary like this one, where you have one value per, let's say, month, and apparently this is a number of airline passengers over the years. But you can have also something very, very different in terms of frequency, like this one. These are sound waves, and you will have around 22,000 samples per second. Or you can have something similar or something different like this. That would be a trajectory over time. So it means that you will have like 3 different values for each time step, and it will be somehow correlated because it's a movement through a physical space. Or you can have something like this candlestick chart that would be a aggregated value, and you can actually create such a thing for a different periods in time, whatever you like. And of course, there will be different models for dealing with this different temporal data. And also there are different tasks you want to do with your time series. So for example, naturally, you would like to know the future. So you want to do a prediction, or you want to do a classification of a time series into a set of classes, or maybe you want to look for anomalies in your time series, or maybe you want to create synthesize another time series from a different one, and doing something like a speech synthesizer. And so it means there will be also different models. And let's start with a classical approach, because I think that the classical approach is still valid. It can tackle some specific things like this one, which was this number of airline passengers. And if we are talking about forecasting or predicting to the future, then the classical analysis is still useful, and it'll be all about like decomposition and finding factors like inflation or trend or seasonality. And what you're trying to do is like remove these factors out of the data. And when you do this, then the rest, which is something like this, you can call it, well, let's say it's just a noise, and you can measure the mean value for that noise and say, okay, I'm going to approximate it to the future with a constant value, and then add everything back and create a pretty decent prediction out of it. Or what you can do is apply some of these classical models that will try to predict from the time series past, and you can create quite decent prediction like this one. And I will strongly recommend who are interested in forecasting for time series to actually read some materials. This one is pretty useful. There's a lot of information there. And one of the reasons is that it set quite a good baseline for you. And also, it's not really difficult today. And it's just like importing a package in Python if you want to play with that. And it's pretty easy. Of course, there are cases which are not so easy and can't be really done with classical analysis. So for example, this one would be taken for a hydrology domain, and you have 2 different time series. The blue one would be a rainfall, and the orange one would be a runoff, the amount of water flowing in a river at some point down the stream. And why I choose that is because there are very long nonlinear dependencies between the input series and the output series. And this will pose quite a problem for a classical approach because of these long dependencies. While I can actually use it and try it, this will probably not work. So what we can do, and now we would leave aside that there would be probably a analytical model used for such in a scenario. Now we're just going to go with a data-driven models like machine learning and neural networks. So what we can do, we can just take a classical neural network, the feed-forward one, and stick it in between the inputs and the prediction. And you actually have all these layers and nonlinearity activation functions there, and these long dependencies from one end to the other end, and it will work. Well, it will work, but there are issues. The first issue for this time series case is you have also these connections from the end to the beginning, which means that you're effectively using the future for predicting the past, which is not really cool when you're dealing with time series data. Well, you can rephrase this and use maybe just a part of the inputs to predict something in the future, but still there are other issues, like it's fixed in time, or the window is really fixed. You can't really stretch it. And actually you are learning over and over the same model for each output neuron, and you don't want to do that, right? And that's actually why you would like to use something like recurrent neural network for time series analysis, because these little cycles here that actually creates a memory, like Jirka already said. So this memory can hold some data, and what you're going to do is apply that same neural network, the recurrent one, for each time step in the time series, and it's actually free to any length of your time series, which is what you're looking for, and it's much smaller. Of course, it comes with its own issues. For example, it's really slow to train it, because what we use for training these kind of models is backpropagation through time, and through time means that you have to have a copy for each time step in a time to be able to let that learning signal going through the network back. And that's why it's almost impossible to parallelize it, and that's why it's so slow. Anyway, that's not the real problem, because, well, you can always throw it more computers on that. The real problem was that there is something called vanishing gradients. When you have this learning signal and it goes through the network back in time, it needs to go through activation function, and that activation function diminished the learning signal quite strongly. So effectively, after, let's say, 10 to 20 time steps, the gradients, the learning signal is so small that you're hitting the accuracy of the representation of floating point numbers in computers. So it, well, effectively doesn't work. And that was the state of the art until the year 2000, around 2000, where long short-term memory, LSTM, were found by lab Dr. Schmidhuber, I think. And not the only, but the most important part and the most important change is this part here, which creates a straight path without any activation function back in time in LSTMs. And that's why these LSTMs work very, very nicely for longer sequences, even like 10,000 steps back in time. And that was really, really important for things like NLP when you have these long sequences, and that's why it's so widely used for these. And we can also use it for time series, right? So we have a working recurrent network, and we have our long time series and maybe some additional input data. So how we are going to create a training set? So first thing, we are going to create a testing set, and we will take such part of the data, and we are not using it for training. This is really, really important, because you want to make sure that there will be some part of data that the model haven't seen during the training, so you can test it and say, okay, this is going to work in reality, or it's highly probable that will work. So what we are going to do next, so maybe I can take the inputs, just feed it into the network at the inputs, and try to do a prediction on that part here. Well, while I can do that, it will result in like massive overfitting on that part, because LSTM are really good in creating a precise sequences at the output. And I don't want to do actually that. I want to have some understanding of what's going on there. So instead, what I'm going to do is like sample smaller chunks, like a local time series, and accompany this with even smaller parts used for prediction. I will add some additional input data, and I have to be very careful about not putting like these local like future data to the inputs, because it will again spoil the whole model. Another question is how long these chunks should be. And the answer is quite different for a different domains, so you have to experiment. But for the training for a model itself, it doesn't really care that model doesn't really care that much, because you can train it on sequences of different lengths altogether. Yeah, so we can create such kind of a training set. There will be some padding or truncating or something like that, but it doesn't really matter for now. And you will also take these target values you want to train on, you'll unfold the network and feed it like this. And as you can see, I'm not using here these intermediate outputs. I'm just using the prediction to be like feed here, and I want all the prediction to be out of here, which I can do maybe for fixed window or prediction, why not? Which actually opens another question, like how many different architectures are there for sequence data? So, well, the first one is quite boring, is one-to-one, which is like no recurrency at all. The second one just saw is like many-to-one. I have many different inputs. I will let the network to create a representation inside and then ask for an output and learn on that. I can take this and turn it upside down to have one input and then many outputs. That would be something Adam presented as like image captioning. They do have an image, and the model needs to understand and then create a sequence of words. Or I can have a many-to-many case, like that one at the beginning when we are predicting in each time step a runoff in the river from the rainfall information. Or I can have something like this, which would be that image, that machine translation Jirka was referring to in his talk, when the model needs to know the whole sequence, then create a representation, and then create a output sentence, because I need to know what this sentence is about in a different languages, right? And so these are some of the architectures, like really the basic one I can do with the sequence data. And this actually the recurrent networks, the main principle is that they are adding temporal notion to, well, any underlying architecture I can imagine. So if I have image frames, if I have images, I can apply a convolutional net to understand these images separately and then stick LSTM on top of that, and I can create a video clip classification model out of it. In this part, it would be probably something like a tricked classifier or something like that. Or I can take a more abstract or artificial image, like a spectrogram, which would be a graphical representation of sound. And I can use convolutional nets and stick an LSTM on top of that and let the network at the top decide whether it should output a word or just wait for more data and output the word after that and create a speech recognizer out of that. Also, you can replace this part with something different. So for sound, you can use something like a gamma tone bank or something like that, which is known to actually work. So the LSTM, this temporal part usually sits on top and gives it that temporal notion. So my last example would be predicting let's say a stock market movement from a textual data. And if you want to do something like that, and you will try to connect it directly, it effectively means that you're trying to learn a foreign language written in a foreign script out of the looking at the red and green bars, which is really, really difficult. So you're not going to do that, but first what you're going to do is you're going to do a pre-training. And as Jirka mentioned, there's something like a sentiment analysis task. When you create a model, maybe I will choose these word-to-vec embeddings as a first layer, then stick an LSTM on top to be able to read the whole sentence of a specific tweet. And then I have a database of sentiment labels, so it's positive or negative or neutral, and I will use it as a pre-training for my model. Then I will take that trained model, I will rip off the top layer, because I'm not interested in that binary signal telling me if it's positive or negative. I'm interested in that understanding that needs to be in that model to some degree. That model needs to know how to create it and sentiment signals. So I want to reuse that for my target variable, which would be that prediction from that stock market data. So I will also feed the history of the stock market to that LSTM, and I will do the fine-tuning on that, so the learning signal actually travels through that LSTM on top. And I can choose to actually let it travel down to change that that language representation which is there. I don't. It won't be like learning the image from scratch. It will just like fine-tuning to understand it more like a business type of text or something like that. And well, that's it. Thank you very much. And I think that we will have now a discussion. So thank you very much again.